Jimbo's meowing too. Hello everyone, it's November the 10th. Alrighty. Alright, look at what we have today. So they're recycling the same problem. I've done this so many times. The best time to buy and sell. Oh, well, actually, this is number 2, right? No, then I haven't done it many times. Number 2, I think I only did it once. But anyway, I think the last time I did it was what, like a week ago? Could be a week ago. So nothing too difficult. I think I still remember it. Oh. Alrighty. It seems like I need to restart my laptop. Jeez, it's so slow. Unbelievably slow. I can't even open my Sublime. That's ridiculous. Come on. I try to open Sublime, I can't even open Sublime. There we go. Took like what? I don't know. Yeah, I need to restart a laptop. Actually, I think this should be a thing. I need to restart every single day. This laptop is so old. It's like, what, 6 years old? No, 7. The laptop is from 2017. No, 17. 14. 2014. What am I doing? Come on. Oh, just delete this. Let's see if we can just do one round. Wait, what is so special about this one? This is only hold at most one share. You can buy immediately. I think this is as many times as you want, right? I think this is as many times as you want. So we have a holding state and an empty state. Holding state is going to be, the way I like to do it is we're going to do math.inf for holding state. Empty state will be 0, right? And then just for P, for pricing prices, holding state and empty state. Holding state will be maximum, either holding state, so with no action, or is the empty state gonna buy, so minus P. An empty state, it could be max empty state, no action, or holding state plus P. And we're gonna return empty state. Yeah, I think that's the one. Alright, let's check. We have this, we'll return 7, right? And then this one will return 4. This one will return a 0. Okay, and that's it, right? We have, yep. This is going to be prices. The max profit prices. Yep, I think that's it. Alright, let's put in here. Run it. And submit it. I kind of see, when's the last time I do this? 6 days ago. 6 days ago is the last time I do this. So, this is, oh, we're at 495 today. 495 days. We got a 68 milliseconds. This is the same. This is state machine, right? State machine. ON 68. 42. So 2 something, right? 122. 122. Okay, all right, let's roll another one. Yeah, I mean, I done this 6 days ago. I done it 6 days ago, so it's a stock purchase and sell problem. So I done 1, 2, 3, 4, 5 of them many times. So it's an old question. Old question. That's fine. I mean, we're settling to this new attempt at finishing as many problems as we can. So it doesn't really matter if they use an old question. I mean, it does pose more challenging, right? So the challenge is if it's an old question, then I need to do it as fast as I can so that I can roll another one. But come on, the stupid laptop is so slow. So slow. All right, the second page. All right, so what do we have? Oh, we're almost done on the second page. We have factorial trailing zone, zones of zeros. No idea what this is. All right, let's take a look. All right, factorial trailing zeros. I think I done this like when I was a kid. All right, you're just playing with your calculator. I done with this, like the number of zeros at the end. The number of trailing zeros in this. Okay, so the first trailing zero happens at 5, right? 10 to the 4th. I mean, oh, logarithm time. I mean, we can just call. Yeah, that will be. That will be the one that I will use if this is in a real engineering. Like you just use Python has factorial and it can handle large integers, so you just call factorial on the large integer and turn the integer into string, and then go from the back to the front to count how many trailing zeros there are. But we're not going to do it that way, right? We're not going to do it that way. We are going to try to do logarithm time. Okay, logarithm time. So how do we approach this logarithm time? Well, logarithm time, it feels like binary search, right? Can we binary search this? How do we binary search this? Probably not binary search. I mean, it could be like every time we have a 0, we can actually remove the 0. But that's not logarithm time. Logarithm time is divide and conquer, right? So we have n, but divided into 2 halves, right? Because the number of zeros, yeah, maybe that is the case. We divide in half, right? So given a value, let's say 10, right? So we divide in half. 5, so factorial, so 1 to 5, and the second will be 6 to 10, right? And then we divide in half again. 1 to 5, we divide it 1 to 2. Actually, 1 to, if we 1 to 3, 4 to 5, and then that'd be 6 to 8, 9 to 10. 1 to 3 we'll divide into 1 to 2 and 3. 4 to 5 we'll divide into 4 and 5, right? 6 to 8 will be 6 to 7 and 8. 9 to 10 will be 9 and 10. So once we are by itself, we just return itself. And then so 1 to 2. So everything will go down, right? So we'll return itself. Oh, wait, this? Is this? Is this O n log n or is O log n? Talk about merging cost, right? Because the recursion cost is log n. Merging cost, if merging cost is O1, then this is going to be log n. So merging cost is, we multiply them together and count how many zeros there are. So we're going to return the number of zeros, right? So number of zeros is 0, number of zeros is 0, and then if the number of 0 is 0, then the multiplication, we have to do the multiplication too. So we do the multiplication, right? And then plus the number of 0, and then we return. So all this branch can be 0. 4, 5, but 4 times 5 will be number of zeros 1. So come here. We have to return two things, right? First is the product, and the second is the number of zeros. So the product times together. The product and the product times together. Oh, so we're gonna remove the 0. Right? We're gonna remove the 0. So when that times together, the maximum 0 is going to be 1. Hold on. We can time together and can we just do log? Hold on. Can we just do log? Like, what's... No, that's 10 to the... Yeah, like, we do log 120. It give us 2. Log 120 give us 2. Okay, that's probably... Give mod 12, right? So 12. Oh, I think it's we try not to multiply them together. That's the ON part. Okay, so we get, and then we multiply together. And then we multiply it together. So basically, we're trying to say we can do O log n to multiply them together, and then what? Divided by 10. Divide by 10. No, it's not divided by 10. So we do keep count. How do we keep count? The number of zeros. Well, if two values, they do not have 0 in them, then their multiplication at most can produce 1 0. Is that true? Is that true? Basically, just like, because it's all about, no, that's actually not true. Wait, is that true? If a value is not ending in 0, I think I can find like maybe a 202 times 5. Oh, wait, no. Two values multiplying, right? And then we can only produce 1 trailing 0. I don't know. Is that the way to go? Like, and each one will multiply, so we'll find the number of zeros from left, number of zeros from right, and then when they come back, we have the product and product, and then I'm going to multiply the products together to get to me. But those product are modified such that they don't have trailing zeros. So when they multiply, then we can just simply do div mod on 10. Oh, not div mod on 10, just like mod 10, right? If mod 10 can be divided, that means we have one trailing zero. So yeah, that's the thing. Two values multiplied together. How many, if they don't have trailing zeros, how many leading zeros can we get? Let's see. Say we can get 1 0 here, right? And then this times this plus this, then might get a 0. Yeah, I think that's possible. So that's like this. That's not gonna get 0 though. Yeah, the only way to get 0 is ending with 5, right? Ending with 5. And then we multiply by an even number, right? By an even number. Like 25 times 4. There we go. Yeah, that's your counterexample. 25 times 4. We can produce 2 trailing. So what? Yeah, how do we maybe we can analyze it? Hold on, let me think. So 1 times 2, 1 to 9, right? 9 factorial has only 1, right? And then we times 10, we got 2. 19 factorial. Oh, it's too big. Can see. Yeah, my issue is just, I have two values multiply, and if they don't have trailing zeros, and then their product, how many zeros? But if we can count the number of zeros in O1 time, then this one will also work, all right? If we can count in O1 time. If we can count in O1 time, we just multiply them. Oh, I cannot, because that will be On. We want to do O log n. Well, the merging cost. This merging cost? What is the merging cost? And merging cost is O1. So we have multiply, we have, how do we get the number of zeros? Given a value, how do we get a number of zeros? Maybe we can, I don't know, like log. Log might work, right? So log 200 is 2 point something. That's 2 trailing zeros, right? Well, anything larger than 100 will give you 2 point something, right? Until 999, that still give you 2 something. So that means given any value, right, from 100 to 1000, within this range, everything is 2 point something. So everything only has 1 trailing zeros. Well, actually no, because we have 200, 300, 400, all right? So we don't know. Oof. I mean, we can do a log. So we're given a value, we do a log on the value. All right, we do a log on the value, so we know potentially how many zeros they're gonna be. But then what? Then, no, that's not helping. That is not helping. No, I don't think this will actually make it faster. All right, let's think again. So we have 1 times 2 times 3 times 4 times 5, right? 6, 7, 8, 9, 10. So all the 10s they contribute, we can just take it out. All the 1 has 10, so like 10, 20. Oh, 20 is 2 times 10. All right, 30. How about this? Like all the even numbers, because odd numbers do not contribute at all. So we only need to handle even numbers. Okay, so 2 and 5, right? So 2, 4, 5. So all the 5, everything related to 5. 5, 10, 15, 20, 25, all the way. So we can find all the 5s. And then we find all the even numbers in between. 2, 4, 6, and 10. 8. Let me think. What will be the best way to handle this? So the 5s will be 1 times 5, right? 2 times 5, 3 times 5, 4 times 5, all the way to whatever value times 5, right? So times 5, that's all the 5s. And then we're going to have for the even numbers 2, 4, 6, 8, but not 10. I'm going to skip 10, so 12. So what's the game plan? Well, the game plan is to see how we can make them create more zeros. Well, they're going to be more non-zero even numbers out there. And even numbers basically is just contributing. It's just contributing. If we can find all the 5s, right? All the 5s. Okay, let's find all the 5s that's inside. All the 5s. How do we find all the factor of 5? Given a value, I know the largest. I know all the multiples of 5s. Yes, I know. And then from all the multiple of 5s, can we get the total number of 5s? Well, 5 is a prime number, right? So 1, 2, 3, 4, 5, right? 6, 7, 8, 9, 10. 10 is another one, right? So basically, every 5 times, we're gonna get another 5. And then, every 5 times, we get another 5. So 5 times 5, that's 2 5s, right? And then 5 times 5 times 5. Let's make this like unnecessarily convoluted, right? Let's see how convoluted this is. Yeah, I think what I'm trying to do is to find how many singular 5 factors there are, and how many singular 2 factors there are. And then the goal is the count number of zeros is just the smaller. is actually the how many singular 5 factors, because the 5 factors will always be smaller than the total number of 2 factors, right? That means for every single 5, we shall be able to find a 2. That was my guess. Is that a correct guess? Every single 5. Well, what we have is all the even number times 5. We already counted, right? We already counted all the even number times 5 inside this already. Some of them can produce 2 zeros. I don't know. It still feels convoluted. Let's go back to the divide and conquer. So divide and conquer, I need a product, and a product will multiply with each other. Then I need to count the number of 0 of that. So it's just like, how do we do that? Count the number of 0. Well, what we can do is, if it's an even number, we return the number of 2's. If it contains a 5, we return a number of 5's. The number of 2's and number of 5's. How about that? So we break down 1. So 1 will return nothing. So the number of 2's and number of 5, that's what we want. So if it's 1, that's going to give us 0 and 0. If it's 2, we have to say, well, 1, 2, and 0, 5. So 2 counter is 1, 5 counter is 0, right? 3 comes up, going to be 1, no, 0 and 0. And then they're going to multiply together. Oh, it's not about, we just add them together. We just add them together. So again, we have 1, 2, 0, 5. 4, all right? 4, we have 2 2's. How do we do that? How do we count number of 2's? Log it, all right? Log it. Hold on, is the log working for that? Like, let's say 36. I want to find how many 2's are there in 36. Can I just do log 36? Log 36 divided by log 2? No. No. That gave us 5. All right, that gave us 5, but that 36 only contains 2 2's. Huh. So we need to figure out a way to count the number of 2. I mean, we can just, but is that still? Well, if we divide it by 2, divide by 2, divide by 2, all right? That's how we're going to find how many 2's there are. Well, we can also do like divide by 2, and then divide by 4. The same thing with 5. Count the number of factors. Okay, number of factors. How do we count number of factors? Yeah, we can just divide? Because it's only to 10 to the 4th, right? Even if we do that divided by log 2, that's 13 times. And at most, we go 13 times. So that's considered O1, all right? So we can count number of 2s and number of 1s for every single, right? For every single, so 4, we'll just do divide by 2, divide by 2, right? And that considers log, that's a log. So we have 2 2s and 0 5s, right? And then 5 is 0 2 and 1 5. And when these combine, they're gonna produce 2 2s and 1 5. And then when I combine the left and right, we're gonna have 3 2s and 1 5. Okay, so the left branch gives us 3 2s and 1 5. So eventually we're just gonna count how many the smaller value of the number of 2 and the number of 5. Like on the right side, we only have 1 5 because 10, we only have 1 5, but we have a bunch of 2s. We're always gonna have more. Yeah, like I said, we're always going to have more 2s than 5. So we only need to count number of 5s, right? We only need to count number of 5s. So yes, we just need to count the number of 5s. How do we count the number of 5s? Well, we have n, right? So we know the total number of 5s. So we need to count the total number of 5s, then total number of 25s, and the total number of 125. Yeah, that should be it. The total number of 5s, which can be calculated just by, I think, just divided by 5, right? The total value divided by 5. So we can say the total number will be the n, right, divided by 5. N divided by 5 is the total number of values inside that contains at least one factor of 5. Yes. And then we do n divided by 25. That's at least 2, right? So we have to add that. So eventually, we're going to go all the way to log n 5. That's not log n 5. Yes, it's log n 5. So we know how many power 5 need to go to. So we do log. Actually, we can just loop it. Oh, I have an idea. All right, let's try it. This is how should I say it? It's interesting actually. Yeah, it takes me a while to. I'm not sure if it's right, but I have a confidence. All right. Here's what I think. All right. Here's what I think. Trailing zeros. So we're gonna count the number of 5s. So we're gonna say num res actually 0, right? And then pow p equals 1, right? And then we should say while 5p is smaller or equal to n, res plus equal to n divided by 5p. Yeah, we come up p plus equal 1. I can just do. Now I want to avoid using log, right? So we just use this, come back, and then once it break out, then we need to return res. Okay, let's try this. So if it's 3 is gonna be 0, right? 3 is 0, 4 is 1. No, 4 is not 1. 5 is 1. Wait, no, 10 is 2. And if n is 0, that's going to be 0. We can actually test this by, if this one doesn't work, we can just, write our own test case and then try it. Trading zeros. Yeah, these are right. I mean, let's run our own test cases. All right, let's run our own test cases. Yeah, this is just stupid. Let's run our own test cases. So tests equals to list range 1 to 10. No, actually 10,000. Right, 10,001. Right, that's our test. And then there's no answer. We're just gonna have in in this. All right, rest is this answer. How do we get answer? Well, answer is just going to be factorial. So I'm gonna give factorial. Python factorial. I think it's in the math module. Math of factorial. Okay, so we just say import math. So I'm gonna say math.factorial n, right? str this thing, and then we're gonna count the number of zeros at the end. How do we do that? Well, we can do answer equals to 0, right? And then fact str equals to this, and then we say and what would be the easier way to, we can just strip. Yeah, we can strip 0. We can write strip. Yeah, so how about this? We're gonna say fact str.write strip, right? We're gonna strip out the 0, and after that we're gonna just say len this, right? And we'll say factorial str minus, so len factorial str minus this. That's gonna be our answer, right? And then, all right, let's not be too ambitious. Let's go like 100. Well, yeah, 1,000. Well, let's not print this because I need to see. Yeah, and then 10,000. 1. That'll take a while, but it's fine. Yeah, I think this one is correct. Damn, look at this. It'll take a whole lot of time to do this. That's why even if I use this, it's not gonna pass. It's not gonna pass. Screw it. Let's just go for it. Submit it. There we go. Nice. So cancel. All right, and this is not gonna. 1,000. We can do 1,000. All right, 1,000 is fine. All right. So the idea, right? Let's go chief key, recipe. All right. So the idea. Okay, LeetCode 172. It took me a while. Yeah, it took me a while to figure out what. Yeah, it took me a while. Took me a while to figure out the trick in this problem. Well, the requirement, right? The requirement is to do it in log time. Thus, we cannot simply compute the factorial for each n. Now I was thinking about divide and conquer, right? Divide and conquer. But this still requires counting the number of zeros at each subtask, right? At each subtask. So that does not seem to simplify. All right, seem to simplify the problem much. The insight came when I realized that the only combination to create a trailing zero, right, is 2 multiplied by 5. And since there are a lot more factors, a lot more 2 factors, right? 2 factors in factorial than 5 factors. Thus, the number of trailing zeros equals the number of 5 factors. In other words, we only need to find all the 5 factors from 1 to n. So we start with factor of 5, right? We'll start with 5k, right? With number of values in the form of 5k, then 5 squared k, 5 times k, 5 times k, then 5 squared times k, then 5 to the third times k, until we exhaust, right? Until we exhaust, until 5 to the whatever is larger than n. For each form, the number of 5 factors, the number of additional, that's the key, additional 5 factors is n divided by 5 to the whatever power. And that's it. This is O log n. Well, technically it's log 5n, right? This one runs at 20 milliseconds. 20 milliseconds. Or a 99. Ooh, we hit a 99% ranking. Wow, I haven't done this for a while. Alright, so let's check this first and then go to discussion. One-line solution in 3 languages. Ooh. But sometimes one number may have several 5. Example, It's always ample, so just count how many 5. So else n divided by 5 n divided by 5, that's a number of 5s. And then we do self.trailing zeros, n divided by 5. So we're moving down. So let's see, what is the logic? So every time, so the first round is 5k, right? 5 factor of 5. We get a total number. And after that, we need to find a factor of 25. So I said call self.trailing zeros, n divided by 5. Well, this one just moved the top lower. Okay. And then we do n divided by 5 again. Hold on, we do n divided by 5 again. Well, that is equivalent to n divided by 25. Right? That's equivalent to n divided by 25. And I did n divided by 5 again, so the next one is n divided by... so like every single time, we just count n divided by 5, which is here, and then n divided by 25, and n divided by 125, and all the way down. Ooh, nice. Very, very smart. Very smart. Alright, I like the solution. I like the recursion. So it is. So we did hit the correct answer. So this one, recursion, very smart. Very, very smart. Same idea, but the implementation is very smart. So just return 0, right? If n equals 0, else n divided by 5 plus self-calculating 0, n divided by 5. Boom! That's it. Yep. Ooh. Nice. Let's see how fast this one runs. I think some people want to do this. You know, it tells you to try to do it in log, so you have to do it in log. Nice. All right, that's it. Yeah, let's just end it here. We have some time. I don't want to do another one today. I'll see you guys tomorrow. Adios.